So, when you're looking at a spreadsheet, just packed with data, maybe sales figures or market trends or even just numbers from your own budget, and you're thinking, there's got to be a pattern here somewhere. How do you actually figure out not just if things are connected, but like how much they are and if that connection is even, real? Welcome to the deep dive. Today, we're really digging into something called linear regression. It's a fundamental tool for tackling exactly those kinds of questions. Our mission: to unpack your sources and get to the heart of how we measure relationships in data, how we figure out how good our explanations are, and crucially, if the results actually mean anything statistically. Think of this deep dive as maybe a shortcut to understanding three really key ideas that pop up everywhere in data analysis.
Yeah, and what's really interesting here is that, while the math can get a bit nitty-gritty, as one source puts it, the core logic, it's actually very clear. We're basically talking about a method to find a relationship, see how strong it is, and then check if it's likely just random noise. The aim is really to go from just looking at data points to making reliable predictions and drawing solid conclusions.
Exactly. And your material breaks this down really nicely into like three main steps. First up is least squares. That's the technique for finding the best fit line or even a plane for your data. Then second, we'll get into R squared. That tells us how much of the variation in your data the model actually explains. And finally, we'll tackle the p-value for that R squared, which is super important for knowing if what you found is, well, statistically significant. Okay, so let's start with the first big idea. How do you even draw the best line through a whole cloud of data points? It sounds maybe a bit like guesswork.
Yeah, it might seem that way, but there's actually a really powerful and honestly elegant method called least squares.
And your sources use a great example for this, right? The mice.
That's right. Imagine you've measured the size and weight of a bunch of mice. And the goal is to predict a mouse's size just based on its weight.
Okay, so I'm picturing these dots on a graph. Each dot is one mouse, showing its weight and size. If I just sketched a line through them, how do I know if it's any good?
That's where this concept of a residual is key. The residual is just that vertical gap,
Yeah.
the distance from each actual data point, each mouse, down or up to the line you drew. It's basically the error for that specific point, the difference between the real mouse size and what your line predicts it should be based on its weight.
Gotcha. So it's how far off your guess is for each mouse.
Exactly. Now, the least squares process, it's systematic. You start with some initial line, any line really.
Okay.
Then for every single data point, you measure that residual, that error.
Right.
And here's the clever bit. You square each of those residuals.
Square them. Why square them?
Well, squaring does two really useful things. First, it makes all the errors positive, right? Doesn't matter if the point is above or below the line. Second, it gives much more weight to the bigger errors. Points far away from the line have a much bigger impact on the calculation.
Okay. That makes sense. So big misses count more.
Precisely. Then you just add up all those squared residuals. That total, that's your sum of squared residuals.
Okay, so I have a number that represents the total squared error for that line.
You got it. And the least squares magic is that the method then tweaks the line. It rotates it just a tiny bit. And with each tiny adjustment, it does the whole process again. Remeasures all the residuals, resquares them, resums them.
Wow. Okay, so it keeps adjusting and recalculating.
Until it finds the one line, the specific angle and position that results in the absolute smallest possible sum of squared residuals. The least squares. That's your best fit line.
That's actually really neat. It's like finding the line that minimizes the overall error.
Exactly. It's foundational because it's not just any line. It's the line that statistically gets closest to all the data points overall. It gives you the most precise guess you can make about one thing based on another. So the result is a specific line with an equation, like y equals intercept plus slope x. And that slope tells you the relationship, like how much bigger mice tend to get for each extra gram of weight.
Okay, great. So we've used least squares, we found our best line, we have our guess. But I mean, how good is the guess? Like, how much does knowing a mouse's weight really help predict its size compared to, say, knowing nothing? This is where R squared comes in, and it gets really interesting.
It does. To get R squared, you first need a baseline. What's the variation if you know nothing about weight? Your best guess for any mouse's size would just be the average size of all the mice, right?
Right, just a simple average.
So you calculate how much the actual sizes vary around that average line. Your sources call this the sum of squares around the mean, or SS mean. That's like the total variation you're starting with.
Okay, the total amount of size difference we're trying to explain.
Exactly. Now, compare that to the variation left over after you fit your fancy least squares line. That's the sum of squares around the fit, or SS fit. This SS fit measures the variation your line didn't explain. It's the leftover scatter, the noise around your best fit line.
Okay, so SS mean is total variation. SS fit is the variation the line couldn't account for.
Precisely. And R squared basically tells you how much variation your line did account for. The formula is essentially total variation, unexplained variation, total variation, or SS mean, SS fit, SS mean.
Ah, so it's the reduction in variation you achieved by using the weight information expressed as a fraction of the original total variation.
You've got it. It's the proportion of variance explained.
And it's usually shown as a percentage, right?
Yep. So an R squared of, say, 0.6 means 60%. It tells you that 60% of the variation you saw in mouse size can be explained by differences in mouse weight.
And R squared 1, that's 100%.
Perfect prediction. All the data points fall exactly on your line. Weight perfectly predicts size in that case.
And R squared equals 0.
Means your line is no better than just using the average size. Knowing the weight tells you absolutely nothing more about the size. The line is probably flat.
So is there like a good R squared value we should aim for?
Well, that's the tricky part. It completely depends on the field you're in. You know, in physics, doing a super controlled experiment, you might expect an R squared of like 0.9, 0.95, or even higher.
Okay.
But in fields like biology or social sciences, psychology, where things are way more complex, an R squared of, say, 0.3 to 0.5, 30% to 50% could be really meaningful. It shows a definite relationship, even if lots of other factors are also involved.
Right. Context matters a lot.
Yeah.
Okay, so R squared is useful. Now, what happens if we make things more complicated? Like instead of just weight predicting size, maybe we use weight and tail length to predict body length. Can R squared still handle that?
Yes, it can. But now you're not fitting a line anymore. With two predictors, weight and tail length, you're fitting a flat surface, a plane, through your data points in 3D space.
Whoa, okay, a plane. And if I added even more predictors?
Then it becomes a hyperplane in multidimensional space. Hard to visualize, but the math works the same way.
Okay. But does adding more stuff always make the R squared better? Like what if I added the mouse's favorite color? That shouldn't help predict size, right?
Yeah, right. It shouldn't. But here's a potential issue. Standard R squared can sometimes go up just by adding more variables, even totally useless ones like favorite color or, as one source puts it, flip of a coin. Least squares will try its best to fit something, even if it just sets the effect of that silly variable close to 0. It doesn't penalize you for adding junk.
Huh. So just adding more colors to my spreadsheet could make my R squared look better, even if the new stuff is meaningless? That seems like a problem.
It is, and that's exactly why statisticians often use something called adjusted R squared.
Yeah.
Adjusted R squared is clever. It basically modifies the R squared calculation to account for the number of predictors you've thrown into the model. It penalizes you for adding variables that don't really contribute much meaningful explanation.
Ah, okay. So adjusted R squared tries to give a more honest picture when you have multiple predictors.
Exactly. It helps you avoid fooling yourself into thinking a complex model is great just because the regular R squared went up a tiny bit from adding noise. It pushes towards more parsimonious models, simpler ones that still explain things well.
Parsimonious, okay.
Yeah.
Use only what you need.
Pretty much.
Yeah.
But this raises another crucial question. Even with adjusted R squared, how do we know if the relationship we did find, the variance we did explain, isn't just a complete fluke of our particular data sample?
Right, that's the final piece, isn't it? The p-value. Let's say we get a great R squared, maybe even an adjusted R squared looks good. Does that mean the relationship is definitely real?
Not automatically. Think about this extreme case. What if you only measured 2 mice?
2 mice, okay.
You can always draw a perfectly straight line between any 2 points, right?
Yeah, sure.
So your R squared would be 100% perfect fit. But does that mean weight really predicts size based on just 2 mice? Probably not. It's just a mathematical quirk of having so little data.
Ah, okay. So a high R squared, especially with small data sets, doesn't guarantee a real effect.
Precisely. And that's where the p-value comes in. It specifically tests the statistical significance of your R squared. It tells you the probability that you'd get an R squared as high as you did if, in reality, there was no relationship at all between the variables.
Okay, so how does it figure that out? You mentioned an F statistic.
Yeah, the p-value for R squared comes from this S statistic. You can think of the F statistic as kind of a signal-to-noise ratio. The signal is the variation your model explains, related to the R squared. The noise is the variation your model doesn't explain, the leftover errors, the residuals.
So F is like explained variation divided by unexplained variation.
Basically, yeah. A good model, where the predictor actually helps, will have a lot more explained variation compared to unexplained variation, so it'll have a large F statistic.
A big F means the model is doing a good job compared to the noise. And degrees of freedom play a role here, too.
They do. We don't need to swim in the math, but intuitively, degrees of freedom relate to your sample size and the number of variables or parameters in your model. Think of it like this. Fitting a simple line needs at least 2 points, right? Intercept and slope. Fitting a plane needs at least 3. The more parameters you estimate, the more data you need for those estimates to be reliable. The F statistic calculation takes these degrees of freedom into account. A large F statistic is more impressive, more significant, if you got it with plenty of data relative to your model's complexity.
Makes sense. More data gives you more confidence. So how do we get from the F statistic number to the actual p-value, the probability?
Well, conceptually, imagine this. You create thousands, millions of fake data sets where you know there's absolutely zero real relationship between weight and size, just random numbers.
Okay, pure random chance data set.
For every single one of those random data sets, you calculate the F statistic you'd get just by chance.
Right.
Now, plot all those millions of F statistics from the random data onto a histogram. You'll get a distribution showing what F values typically pop up purely due to random luck.
Okay, I see the distribution of fluke F values.
Now, take the F statistic you calculated from your real mouse data. Let's say it was, I don't know, F66.
Okay.
You look at your distribution of random F values and ask, how often in those purely random data sets did I get an F statistic of 6 or even higher?
Ah. So what percentage of the random results were as extreme as my real result?
Exactly. That percentage, that proportion is the p-value.
So if only, say, 1% of the random data sets produced an F of 6 or more just by luck,
then your p-value is 0.01, and that's considered small. It means it's really unlikely you'd see an F statistic as strong as yours if there were truly no relationship. It suggests your observed R-squared is statistically significant.
Got it. So a small p-value means unlikely to be just random chance.
Precisely. In practice, we don't actually generate millions of data sets. Statisticians use theoretical F distributions mathematical curves that represent those probabilities, like the red and blue lines in your source material. And the exact shape of that curve depends on those degrees of freedom we mentioned, influenced by your sample size and model complexity.
So bigger sample size usually helps get a smaller p-value, assuming there's a real effect.
Generally, yes. More data gives the statistical test more power to detect a real relationship and distinguish it from random noise. It reinforces the idea that strong conclusions usually need solid evidence, meaning enough data.
Okay, this is all coming together. So to quickly recap this deep dive, we started with least squares to find the single best line through the data.
Right, minimizing the sum of squared errors.
Then we used R-squared to measure how much variation that line actually explains how good the fit is.
Expressed as a percentage of the total variation, keeping adjusted R-squared in mind if we have multiple predictors.
And finally, the p-value, derived from the F statistic, tells us if that R-squared is likely real or just a fluke of our sample.
Exactly. And as your sources nicely put it, to have a really interesting result, you ideally want both things. You want a reasonably large R-squared, meaning your model explains a good chunk of what's going on, and you need a small p-value, giving you confidence that the R-squared isn't just noise.
Significance and effect size, in a way.
Precisely. The p-value tells you it's unlikely to be random, but the R-squared, or the slope itself, tells you if the effect is big enough to actually care about in the real world. So, armed with this understanding now, it raises a good question. How might you, the listener, approach looking for or evaluating relationships you see in data, maybe at work or in studies or even just things you read about?
Yeah, think about relationships you've noticed, maybe between, I don't know, hours studied and test scores, or marketing spend and sales, or even rainfall and plant growth in your garden. How might you try to quantify them now? What variation are you actually trying to explain? And maybe more importantly, knowing about R-squared and p-values, what questions might you ask the next time someone shows you a graph with a line slapped on it and says, see, they're connected?